So imagine, like putting the 100 smartest human beings on Earth into a single room to solve some massive, complex, global crisis.
Oh, wow. Yeah, that sounds like the ultimate brainstorm, right?
Right. I mean, it sounds amazing until you realize that without a boss or, a strict schedule or even a clear agenda,
They just argue.
exactly, those 100 geniuses will probably spend, like, all their time just trying to figure out who gets to speak next.
Yeah, that makes total sense.
And right now, that exact scenario is what is happening at the absolute cutting edge of artificial intelligence. We're moving away from the era of just a single, isolated supercomputer churning through data all by itself.
Right, the whole single brain model.
Yeah, we're stepping into this era of collective intelligence. So teams of highly specialized AI agents actively working together to solve problems.
But putting a bunch of incredibly smart, specialized AI models into a digital room doesn't automatically mean they're going to collaborate effectively.
Definitely not.
In fact, without the right architecture, they usually just get in each other's way.
And that structural challenge, that's the focus of our deep dive today. We're looking at a super fascinating academic paper from researchers at Nanjing University, the University of Technology, Sydney, and the University of New South Wales.
It's a really heavy paper.
It is, yeah. So the paper introduces a framework called multi-agent coordination adaptation via structure-guided orchestration, which is a mouthful.
Yeah, we are definitely going to just use the acronym they provide, which is MACA.
MACA, right? Yeah. So what's our goal today?
Well, our core mission here is to really understand the mechanics of AI communication. Because whether you are actively managing tech workflows or, building software, or if you just want to understand how the next generation of AI is going to operate, you have to look beyond just how a single AI model thinks.
Right. It's about how they talk.
Exactly. The communication architecture, how these models talk to each other, in what order, under what constraints. That is what actually dictates the ceiling of their collective intelligence.
Okay, let's unpack this a bit. Let's look at why current multi-agent systems are hitting a wall when tasks get complicated. Because the industry is essentially trapped between two extreme paradigms, right?
Yeah, and they're both failing for completely different reasons.
Right. So the first paradigm is what the paper calls structure-centric adaptation. So systems like ChatDev or MetaGPT are built this way.
Right. So in a structure-centric model, the topology is mapped out explicitly before the task even begins.
The engineers basically hard code the exact interaction order, like who talks to whom and when.
Yeah, exactly. It's basically a digital assembly line. A query comes in, the blueprint is handed down, and every AI agent stands at their designated station.
Just to pass the widget down the line.
Right.
But wait, I know a lot of project managers who would argue that a strict structure is exactly what you want for a complex task, especially something like software development. You want a rigorous, predictable process, don't you?
Well, sure, a rigorous process is incredibly efficient when a task goes exactly as planned.
Ah, right. When does that ever happen?
Exactly. The critical flaw with being entirely structure-centric is the total lack of dynamic adaptability. The assembly line is fantastic for building the same car 1,000 times. But if the environment shifts mid-task or an unexpected edge case error pops up, the entire system breaks down.
Oh, wow. So it's super brittle.
Incredibly brittle. The researchers mapped this out beautifully using a predefined loop for software generation. So the structure dictates that information flows from a planner agent down to a coder agent, then to a tester agent, and finally loops back around to the planner.
I mean, it seems like a perfectly logical flow for writing software.
It is, until the coder writes a script, passes it to the tester, and the tester finds a trivial error, like just a missing semicolon.
Oh, right. Something tiny?
Yeah. But in a rigid structure, the coder and the tester cannot just ping each other to coordinate a 2-second patch.
Wait, really? Why not?
Because the hard-coded architecture literally prevents that communication. The structure forces the tester to report the error all the way upstream to the planner.
You're kidding.
Nope. The planner has to reevaluate the entire project state, draft a new plan, and pass it back down to the coder. A process that should take 2 computational steps suddenly takes 10. It makes iteration incredibly slow and computationally expensive.
Oh, man. It's the equivalent of a junior developer finding a typo in a marketing email and having to, schedule a meeting with the CEO to get permission to fix it.
That is the exact perfect analogy.
Yes.
The process becomes the bottleneck.
Wow. And because developers recognize that brittleness, they often try to pivot to the exact opposite extreme.
Right. So the second paradigm is orchestration-centric adaptation.
which is like the anti-assembly line.
Exactly. There is no predefined structure at all.
So decisions on who does what are just made step by step,
Yeah.
dynamically.
Yes, by an orchestrator agent based on whatever's happening in that precise moment.
What's fascinating here is that that sounds incredibly agile and flexible.
And for very small, straightforward tasks, it can be. But as you scale up the complexity of the task and increase the number of specialized agents in the system, that agility completely collapses.
Because there's just too many options.
Yeah. The paper illustrates this collapse with a really relatable scenario. Imagine you have a massive library of specialized agents. Planners, coders, testers, documenters, debuggers.
Okay.
And an unexpected bug occurs mid-task. In this orchestration-centric model, the orchestrator looks at this massive menu of agents and has to guess who to activate next based on the immediate context.
Right, and because the possibility space is so wide, the orchestrator just gets lost.
Exactly. The bug occurs, and instead of activating the coder to fix it, the orchestrator gets confused by the context window and activates the documenter agent.
Oh no, so the bug remains unfixed.
Yeah, the bug remains unfixed, and the system just diligently writes a highly detailed log about how it's failing.
It is hilarious and tragic.
The researchers call this role drift. Without an explicit guiding interaction model, the system just loses the plot.
Think about, like, the last time you were CC'd on an endless chaotic email chain at work where 20 people are chiming in, but no one actually knows who is supposed to make the final decision.
Right, everyone's just talking.
That is role drift. That is exactly what a chaotic AI system is doing when it wastes computational power. So we have an assembly line that breaks when it hits a typo and a chaotic email chain that can't execute a basic fix.
Which brings us to MACA. My paper proposes a third way.
A third way. Okay, I like the sound of that.
Yeah. To find that third way, the researchers made an elegant mathematical shift. They stopped treating rigid structure and dynamic orchestration as opposing forces.
Oh, interesting. So they combine them.
Sort of. They framed multi-agent coordination as a posterior inference problem based on variational inference.
Okay, hold on. We need to bring variational inference out of the academic clouds.
Yeah.
How does that actually work in practice?
Fair enough. So variational inference is basically a highly sophisticated guessing game used in probability.
A guessing game.
Yeah. Instead of the AI trying to perfectly calculate an impossibly complex web of every potential communication path, which would take forever, it makes a structured, simplified best guess at a model.
Right.
It checks how close that guess is to reality and then adjusts. It's like trying to draw a map of a massive city you've never visited by only looking at where the traffic jams are. You infer the underlying structure based on the flow of data.
Okay, I think I'm following.
So Métier treats both the structural rules and the dynamic step-by-step orchestration as connected variables that update each other to get the most accurate final answer.
Let's ground this. Instead of bolting the agents to an assembly line or dropping them in a massive room with zero instructions, Métier is basically analyzing the specific user prompt, building a custom fenced-in playing field tailored for that exact problem, and then letting the players strategize dynamically.
Right.
But only within the boundaries of those fences.
That captures the mechanism perfectly. You provide a specialized arena, and the mathematical engine running that arena is designed to minimize something called KL divergence.
Ah, Kullback-Leibler divergence.
Yes.
For those of us who didn't major in stats, what is that?
In everyday terms, KL divergence measures how much one probability distribution deviates from a reference distribution.
So it's checking how far off track the AI is getting.
Exactly. In MACA's architecture, the system is constantly trying to balance two competing desires. It wants to maximize the task utility, meaning it wants to dynamically find the correct answer as fast as possible.
Okay, that makes sense. What's the second desire?
It simultaneously penalizes the system if that dynamic orchestration starts wandering too far away from the logical structural boundaries of that fenced-in playing field we just built.
Oh, I see. It's like a mathematical rubber band.
Yeah, that's a good way to put it.
The AI can stretch and adapt dynamically to solve an unexpected problem, but the moment the orchestrator tries to wander over to the documenter, when it should be talking to the coder, the KL divergence penalty pulls it back into bounds.
Exactly. It mathematically prevents the chaotic email chain.
Wow. So it bridges the two paradigms. You get the guardrails of a rigid structure, but the step-by-step problem-solving flexibility of an agile startup.
You get the best of both worlds.
But wait, building a custom playing field for every single prompt sounds great in theory. But if you have a library of 100 specialized AI agents, Filtering out the noise to find the right players for that specific field seems like a computational nightmare in itself.
It definitely can be.
How does the system not get bogged down just picking the team?
Well, this takes us to the first active phase of MACA, which they call structural prior learning. The output of this phase is a graph spec.
A graph spec, so that's like the blueprint of the playing field.
Exactly. And the first step to building that blueprint is agent relevance scoring.
How does the system even know which agents are relevant before the task even begins?
To score relevance, MACA calculates the semantic compatibility between the user's prompt and the underlying capabilities of the agents using embeddings.
Embeddings, right. So you can visualize embeddings as like a massive multidimensional map of concepts.
Yes. The system takes the text of the user's problem, factors in the available computational budget, and translates all of that into a specific mathematical coordinate on that map.
And then it does the same for the agents.
Exactly. It takes the background descriptions of all your available AI agents and translates those into coordinates as well.
So it basically plots the problem and the potential workers on the exact same grid.
Then it calculates the cosine similarity.
Which is the angle between them.
Right. It measures the angle between the problem's coordinate and each agent's coordinate. If the angle is very narrow, the agent's capabilities align perfectly with the task. If the angle is wide, they are mathematically irrelevant.
Okay, so once it scores them, the system applies a thresholding gate, right? A parameter they call gamma.
Yep. If an agent's relevance score falls below that gamma threshold, they are ruthlessly filtered out of the pool.
Ruthlessly. But wait, isn't that incredibly risky?
How?
Well, what if a complex software development problem unexpectedly requires, like, a high-level math agent halfway through the task, but MACA already kicked the math agent out of the room at the very beginning to save on processing power?
That's a valid concern.
Doesn't this strict filtering just recreate the brittle bottleneck of the assembly line? I mean, human teams often benefit from keeping an out-of-the-box thinker in the room, just in case.
Sure, but human teams don't pay a latency and financial cost for every single word that out-of-the-box thinker listens to.
Oh, that's a really good point.
AI token economics dictate a totally different approach. The gamma threshold isn't arbitrary. It's heavily weighted by the available resource budget.
So if you're rich, you can keep the weird thinker in the room.
Exactly. If you have an unlimited budget, the threshold might be super lenient. But in the real world, retaining a statistically improbable agent just in case pollutes the context window and confuses the orchestrator.
Because it just adds noise.
Right. MACA relies on the probability that if the task embedding didn't register a need for high-level math, bringing the math agent along will cause more role drift than actual utility. It systematically removes the chaos.
So you don't have 50 agents talking over each other. You only have the 3 that mathematically matter for this specific prompt.
Exactly. But identifying the right 3 agents is only half of the graph spec. You still have to define how they are allowed to interact.
Ah, right. Because even 3 people can form a chaotic email chain.
Exactly. And that is where interaction plausibility estimation comes in. It predicts the most effective lines of communication. MACA calculates directed edge logits.
Directed edge logits.
Yeah, it's essentially scoring the probability of success for every potential pathway between the chosen agents.
But how does it know what a successful pathway looks like before the task even happens?
It relies on a multi-layer perceptron, an MLP neural network, which is trained on a buffer of past high-quality interaction trajectories.
Oh, wow. So it literally looks at the game take of past successful problem-solving sessions.
Exactly. The MLP recognizes patterns. It learns that for a coding task, a communication pathway from the coder to the tester has a very high probability of advancing the goal.
Makes sense.
But it also learns that a pathway from the tester back to the broader planner is highly inefficient.
So it assigns a mathematical probability to every single connection, drawing the fences on our playing field.
You've got it.
Okay, so by the time we enter the second phase of the process, MACA has analyzed the problem, kicked out the irrelevant agents, and drawn a highly optimized probability map of who should be talking to who.
Right. The AI policy now starts executing the task dynamically, but only within this restricted space.
And the paper calls this execution phase token-aware orchestration. Now, here's where it gets really interesting. This is a crucial mechanism.
It is the core of why it works so well.
Why is the token limit treated as a fundamental driver of the AI's logic here? Like, why isn't the token limit just an external rule, like a shot clock in basketball? You play the game, and if the buzzer sounds, you're just out of time.
Treating a computational budget as a simple external shot clock is actually one of the main reasons standard orchestration systems fail.
Really? Why?
Because tokens are not just abstract points. In scaling AI, tokens represent server compute power, latency bottlenecks, and literal financial cost.
Right.
Real money. The researchers discovered that if an AI orchestrator does not internally feel that token constraint as part of its decision-making math, it develops terrible habits.
Like what?
Well, it might attempt to execute an elegant 10-step coordination loop when it only has the budget for 3 steps. It isn't grounded in the physical limitations of the system.
Oh, wow. So how does MACA force the AI to internalize that limit?
By attaching mathematical weights and penalties directly to the coordination pathways. As the AI decides its next move, it looks at the graph spec boundaries and calculates the token cost of the proposed interaction. If the AI proposes a path that will mathematically bankrupt the token budget before reaching a conclusion, the internal penalty forces the orchestrator to literally recalculate a more direct, perhaps less elegant, but fundamentally achievable path.
So the token budget actively warps the coordination space.
Yes, it forces efficiency into the decision-making process itself.
That is brilliant. The AI knows it's running out of oxygen, so it stops taking deep breaths.
Exactly.
Which brings us to the real-world benchmarks. And this is where all this theoretical math translates into massive practical gains.
The results are pretty staggering.
Yeah, the researchers ran MACA through 6 different complex reasoning and coding benchmarks, testing it against state-of-the-art adaptive multi-agent baselines.
And these testing environments required the AI teams to handle highly intricate logic, mathematical reasoning, and actual software engineering tasks, where the models had to write code, test it, and iterate on it without human intervention.
The aggregate numbers are just wild. By combining the structural boundaries of the graph spec with that token-aware internal penalty, MACA outperformed the baseline systems by an average of 8.42% in accuracy and task completion.
Which is huge. In the realm of autonomous software engineering and complex reasoning, an 8.42% absolute improvement is a massive leap in reliability.
But the true breakthrough isn't just the accuracy boost, is it?
No, it's the cost of that boost.
Right. MACA achieved that higher success rate while using an average of 43.19% fewer tokens than the baseline models.
It's incredible.
Nearly half the compute power, half the latency, and half the server cost to get a noticeably better result.
Yeah. Think about a standard baseline AI trying to build a web scraper. It wastes thousands of tokens passing the code around in circles, letting the planner debate the documenter before finally stumbling on the solution or just timing out.
Well, MACA just looks at the prompt, filters the room down to just the coder and the reviewer, maps a direct communication line between them, and executes the code flawlessly in half the time.
Exactly. And for anyone managing AI at an enterprise level or paying the API bills for an AI startup, this paper fundamentally reframes the path forward.
How so?
Well, the prevailing assumption in the tech industry has been that to solve harder problems, you just need to throw more raw compute or more specialized agents at the task.
Right. Just buy more servers and cram more smart bots into the chat room.
Yeah. And MACA proves mathematically that throwing resources at chaotic architecture is a complete waste.
Because it just scales the chaos.
Exactly. By systematically suppressing redundant interactions, filtering out irrelevant agents, and forcing the system to converge stably on a solution, algorithmic efficiency becomes the ultimate driver of intelligence.
Wow.
An optimized communication structure doesn't just save you money on tokens. The reduction in noise actually clarifies the AI's reasoning process.
So the core takeaway of this deep dive is really that the future of collective machine intelligence is not about simulating a giant, noisy brainstorming session.
No, definitely not.
It's about dynamically designing the absolute perfect, most efficient room for every specific problem the millisecond before the problem is solved. It's engineering the silence just as much as the conversation.
That's a great way to put it, which leaves us with a pretty profound concept to consider as these systems evolve.
Oh, what's that?
Well, MACA's entire architecture relies on predicting interaction plausibility based entirely on mathematical efficiency, right?
Right.
It optimizes for the shortest, most effective path to a solution using those directed edge logics and token penalties. But as these models scale up to tackle global, multi-layered challenges, the AI will begin dynamically designing optimal communication structures for itself.
Okay, I see where you're going with this.
Structures optimized purely for token efficiency.
You're saying the AI will draw playing fields we wouldn't design ourselves.
Exactly. We might soon be looking at AI teams collaborating in ways that are entirely alien to human organizational psychology.
Well,
They might develop highly structured communication webs that solve massive problems with incredible speed, but the pathways they use to get there will be completely incomprehensible to the human engineers monitoring the system.
because they aren't thinking like human project managers.
Right. We are giving them the mathematical tools to organize themselves, and they are going to organize in ways only an algorithm could understand.
An alien society of algorithms designing their own perfect rooms. Man, that is a heavy thought to leave on. Thank you so much for joining us on this deep dive into the MO framework.
It was a pleasure.
Keep questioning the structures around you. And we'll see you next time.